All right, so let's say to begin with that I have a basic BJT differential pair, right? So this is VCC, here's some resistance RC, here's where I'm taking my output V out 1, I have an NPN BJT, here's where I'm applying some input signal V in 1, I have my tail current IEE, like so. And then I make my copy of it on the other side. V in 2, V out 2. Here is RC. And there's my power supply voltage. All right, so let's say that VN1 is some DC voltage. Let's just call it V capital CM because it's going to be a common mode voltage. And then some very small perturbation, delta V, right? So I'm talking on the order of a perturbation on the order of a millivolt or two, just a few millivolts. So this is representing effectively our small signal that's being superimposed on top of our large signal operating point, which is exactly how all of these amplifiers behave, right? So what should happen to my collector current in transistor Q1 if I add this small amount of perturbation? I should see a small change in the collector current as well, right? So I could say that my collector current, let's label these guys IC1 and IC2. So IC1 would then be equal to let's say 1/2 IEE plus some small change in the current, right? I'm at some DC operating point and I'm just perturbing it by a small amount. So I have my DC operating point current, which if I'm applying the same common mode signal to both inputs, which we'll see in a moment, this should be the DC level, and then I'm perturbing it by a very small amount. Well, since IC1 and IC2 have to be the same, that means that IC2 must be, or excuse me, since IC1 and IC2 have to add together to equal IEE, that means that the small perturbation I see on IC1, I have to see the exact opposite small perturbation on IC2, which means the voltage present at VN2 has to be my common mode voltage, VCM, minus delta V. So if I raise one by a small amount, I have to decrease the other one by that exact same small amount in order for everything to balance, okay? So this is a fundamental key to the analysis of our small signal. If we did Kirchhoff's voltage law around this loop, we would see that VN1 has to be exactly equal to negative VN2, or at least the perturbations do. So just to be super, super clear here, VN1, lowercase v, showing you that it is the small signal, plus lowercase VN2 have to come together to equal 0 in order for all of our currents to balance out at a specific DC operating point. So with that in mind, now let's get into our small signal analysis. So I'm going to first draw my small signal model for this guy, and it's kind of awful. here I have small signal VN1. Yep, I'm giving myself enough room. R pi 1 plus V pi 1 here's GM1, V pi 1, and the textbook ignores the early effect, but we're not punks, so we're going to include it. So there is my left-hand side. Now I'm going to do my right-hand side. GM2, V pi 2, RC, plus V pi 2, N2, and down. All right. I'm going to call this node right here node X, and it's node X is critical to our analysis. So the first thing that I want to be clear about is IEE, my tail current source, small signal model looks like an open circuit, right? So that's why node X is just some floating potential for our small signal model. Our power supply rails have been converted to AC ground, and everything else is just simple small signal. Okay. All right, so if I apply Kirchhoff's current law at node X, I'm going to get the following results, and I just want to be clear about everything that I'm adding together. So I'm including this current, and 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 this current, because they all flow into node X. And so that is going to give me Vn1 minus Vx divided by R pi 1 plus GM1 times V pi 1, where V pi 1 is Vn1 minus Vx. Then I'm going to have V out 1 minus Vx divided by R naught 1. Then I'm going to have V out 2 minus Vx over R naught 2 plus GM2 times Vn 2 minus Vx plus Vn2 minus Vx over R pi 2 is equal to 0. That's my first KCL expression. Now I'm going to kind of group things up. So I can notice I have a Vn1 and a Vn2 over R pi 1. So that's going to be Vn1 plus Vn2 over R pi 1. Let's see. Minus, oh, actually, hold on. I need to do one other thing here real quick before I do this. So apologize for that. All right, so for a well-designed differential pair, we are going to have perfect matching, right? And the cancellations that we are about to make will not work if we do not have perfect matching. So let me say specifically, for r pi 1 is equal to r pi 2 and gm1 is equal to gm2 and r naught 1 is equal to r naught 2. We can simplify this to be vn1 plus vn2 over r pi plus vm vn1 plus vn2. I'm going to have a minus 2 vx over r pi. I'm going to have a m times vx. And then I have plus v out 1 plus v out 2 divided by r naught minus twice vx over r naught is equal to 0. And since we know that the sum of our input signals vn1, vn2 have to be 0, this guy goes to 0 and this guy goes to 0. And what we are left with is going to be twice vx over r pi plus twice gm vx plus twice vx minus v out 1 plus v out 2, all divided by r naught is equal to 0. Where I got rid of all those extra negative signs by multiplying both sides by -1, just so that we're clear there. Excuse me. All right. So that's the result that I get applying KCL at node X. The next thing we're going to do is apply KCL at each of our collector nodes, right? So to be clear, I'm applying KCL here, here, and here, and then here, here, and here. And one thing that I want to point out, in my notes, I did it in 2 steps, but I'll do it here in 1 step. So if I add all of these currents on the left-hand side in orange together, what am I going to get? 0. If I add all the currents together on the right-hand side in orange, what am I going to get? So what happens if I add all 6 of these currents together simultaneously? It's 0, because 0 plus 0 is equal to 0. This is the exact same reason that we can use the supernode technique. I'm just using it where there's not a voltage source to sort some things out. So applying KCL at collectors gives me V out 1. Dang it, it's about to do that stupid thing, I think. V out 1 divided by, give me just a second, I have to save this, close it, and restart because of that stupid error. So I'm going to have V out 1 divided by RC plus GM1 VN1 minus VX plus V out 1 minus VX divided by R naught 1 plus V out 2 minus VX over R02 plus GM2 VN2 minus VX. Sorry. No, that's right. Plus V out 2 divided by RC equal 0. So that's all 6 of those currents together. And I'm going to group things up. So let's see. So I'm going to have V out 1 plus V out 2 divided by RC plus GM1 times VN1 plus VN2, which we know that this guy is going to go to 0. Then I'm going to have minus 2 GM VX, and then I'm going to have plus V out 1 plus V out 2 divided by R naught minus twice Vx over R naught is equal to 0. And rearranging this guy slightly gives me the expression V out 1 plus V out 2 is equal to twice GM Vx plus twice Vx over R naught, and this whole thing multiplied by R naught in parallel with RC. So all I've done is I've moved all of my Vx terms to the other side, moved my V out 1 plus V out 2 term to the left-hand side, and then I have a factor of 1 over RC plus 1 over R naught on the left-hand side. And if I divide both sides by that, it's multiplying by those two resistors in parallel. Because I have 1 over 1 plus R naught plus, 1 over R naught plus 1 over RC. That factor on both sides. So if I substitute this relationship in, excuse me, to this guy up here where I have V out 1 plus V out 2, what I get is the following expression. So I have twice Vx over R pi plus twice GM Vx plus 1 over R naught twice Vx minus, and now I'm substituting in V out 1 plus V out 2, 2 GM Vx plus 2 Vx over R naught times R naught in parallel with RC is equal to 0. So I have one equation, one unknown. So who can tell me based on this what the value of Vx has to be? Has to be 0, absolutely right. I have a ton of coefficients, all multiplied by the same variable, all added together equals 0, means that my variable has to be 0 at all times. So Vx is equal to 0, which means that node X, even though it is representing the positive polarity terminal of an open circuit, is actually an AC ground, okay? So based on all that work, I can ground this guy out right here. And this is what's going to make analyzing these circuits almost trivial, okay? So what I am going to say is I can take this circuit and I'm going to split it up into two what are called half circuits, okay? And so my first half circuit is going to look something like this. I'm going to call this guy, I'm going to deconstruct my input signal into my small signal differential input voltage VID over 2 on one side and negative VID over 2 on the other input, like we did with our large signal analysis, just doing it on the small scale now. Then I have, this guy is R pi 1 plus V pi 1 GM 1 V pi 1 R naught 1. Here's RC. Here is positive V out D over 2. And so what that AC ground allows me to do is split this guy up really into 2 independent circuits. Particularly matter. So this is going to be negative VOD over 2. Here's RC. Negative VID over 2, R pi 2 plus V pi 2. So, and ground here. All right. So I have split my circuit into 2 half circuits. And if these guys are perfectly matched, my half circuits are absolutely identical. All right. So if I were to analyze, let's just analyze the left half circuit, okay? Can anybody tell me what my short circuit transconductance would be? So if I shorted out VOD2 and calculated the current flowing into that node, so let me draw that just real quick. I'll do it in purple. All right. So I'm shorting out this node and I'm finding out this current I out. Who can tell me what that's going to be? So this node is ground, right? Which means there's ground here. Which means no current is going to flow through that resistor RC because there's no voltage drop over it. Is that a fair assumption? Right? We know that both sides of that resistor RC are grounded. There's no voltage drop over it. If there's no voltage drop over the resistor, there's no current flowing through the resistor. We have ground here and we have ground here, which means that whatever current I out is, none of it is going to flow through that resistor R01 either, right? So I would argue pretty easily that I out is equal to GM1 V pi 1, where V pi 1 is just VID over 2, right? I'm not going to write it like that. I'm going to write it as VN because it'll make it slightly easier to see what's what. So my short circuit transconductance defined as I out over VN is just GM1. Okay. Let's erase this guy. Let's look in and calculate R out. So when we're calculating R out, that voltage is 0. So what do we see? R naught 1 in parallel with RC. From this, our differential voltage gain, AVD, which is going to be the ratio of VOD over 2 divided by VID over 2. That's my output voltage divided by my input voltage. So those over 2's cancel each other out, by the way, meaning that this is representative of the full differential signals, is negative GM1 R01 in parallel with RC. So I would argue that this half circuit behaves exactly like a common emitter amplifier because it's a common emitter amplifier, right? If I redrew this guy based entirely off of its small signal model, I have my input signal applied at my base. My emitter is grounded. And then at my collector, I take my output. And here's VDD. And here's that resistor RC. So based on my half circuit small signal model, what it's behaving as is a simple common emitter amplifier with the early effect included. Right? So using these half circuits, we can break things down into stuff that we've seen before, and we can analyze the behavior of any differential pair in this way, because we know that when we split our voltage, input voltage in half, or the differential part to be VID over 2 and the output to be VOD over 2, this half circuit is fully representative of what's going on in the full differential circuit. So let's do another example. Let's say that I have the following circuit. Here's the N1. Here's IEE. Sorry, we're not with a Mosfet right now. Here's Q1. Here's Q2. Here's VCC. What's my half circuit going to look like? Anybody got any thoughts? All I'm doing with a half circuit. Okay, so actually this I guess technically does require a little bit more thought than the last one, all right? So we did a very large amount of algebra, and we found out that a point on the axis of symmetry of our differential pair amplifier had a voltage of 0, right? So when we did all of this crazy math up here, we found out that this specific point was 0 volts. We found out actually it was 0 volts for the large signal analysis and 0 volts for the small signal analysis. Okay? For the small signal analysis specifically, though, we can actually say that any point along the axis of symmetry should have a voltage of 0. And so let me explain what I mean by that just real quick. All right. As a quick aside here, let's say that I have EN1, a resistor R, this is node point X, a similar resistor R, and then Vn2. And I have the same constraint that I had previously, meaning if I raise Vn1 by some amount, I have to lower Vn2 by some other amount. What is the potential at node X going to be if those two resistors are identical? It's always going to be 0. Effectively, those points of symmetry are a fulcrum, right? So if I hold my pen like this, when I tilt one side up, the other side has to go down by the exact same amount, and I can do it the other way, but the point at which I'm holding it is always neutral. So with that in mind, I could split this guy up like so, with the exact same potential applied at both of those, because that's what I'm doing. And my half circuit here is Q3. Here's V out 1. Here's V in 1. Here's ground. So what does this look like? What's Q3 doing? Let's start there. Is it an NMOS, or excuse me, an NPN transistor or PNP transistor? Or actually, let's not ground this guy out yet. Let's look at it large signal. That would be more representative of the small signal. All right. So we have an NPN transistor acting as an amplifier of some sort because we're applying an input signal and measuring an output signal from it. And then we have this guy up here that's loading it, okay? It is a PNP transistor. Is it diode connected? No, if it were diode connected, VB3 and V out would be tied together. So since it's not diode connected, what the hell is this guy doing? It's a current source. Small signal model, what does that current source look like? Pardon? No GM, right? So with the early effect included, it's just going to look like a resistance R03, right? If we just go back to the notes on current sources that we did before we kicked off chapter 10 for a, I guess I can quickly derive it here. Let's look at what's what. All right, so we have here's Vn, here's R pi 1, V pi 1, GM1, V pi 1, R0 1. Here's ground. Here's ground. Then up here, I have my other transistor. So that's going to be GM3, V pi 3, R0 3. My collector is grounded, or that would be my emitter, sorry, for the PNP is grounded. And then I also have over here, my base is grounded. Here is R pi 3, and here is V pi 3. So there is no voltage drop over resistor R pi 3, which means this current source is providing 0 current, which means all I see is this resistor R0 3. Honestly, I'm slightly worried that you guys aren't just automatically seeing these things at this point, because you have a test in a week. It's going to require you to be able to do stuff like that. So anytime you have a current source, it looks like resistance, the early effect resistance R0. When you have a diode connected transistor, it looks like R naught in parallel with 1 over GM. That is the short and fast rule for how those guys work. Burn that into your brain within the next week. All right, so this R naught 3 is in parallel with this R naught 1. So what's the overall voltage gain of this guy going to be? Negative GM1 times R naught 1 in parallel with R naught 3. Absolutely correct. In my opinion, you can get there using inspection, right? Let me be clear about what I mean by that. Okay. So if we were looking for our output resistance, where VN1 is now grounded, what would we see somebody who isn't grounded? Nicole, you look studious. Tell me what's up. Yes. So I'm looking in through the output voltage terminal, and I'm trying to find what resistance I see, where this VN is turned off. Exactly right. So between here and ground, I have R naught 1. Between here and ground, I have R naught 3. This guy has to be off because V pi 3 is 0. This guy has to be off because V pi 1 is 0. So we are going to have negative something times R naught 1 in parallel with R naught 3. Now let's talk about our short circuit transconductance, meaning I short this guy out and I measure the current flowing in. So I have ground here and ground here. No current flows through this guy. Ground here and ground here. No current flows through R naught 1. We know that this guy is off. So our output current is GM V pi. We divide by Vn and we just have GM1. Okay, so our short circuit transconductance is GM1, and we get the exact result that Brian told us that we should have. Right? Be able to do this quickly. All right, so I got 35 minutes left. Okay, so now let's look at one that is considerably more difficult. I'm not sure if, I know that this used to be a homework problem for this class, but I think Dr. Batari might have axed it because he says it's too difficult. So let's prove him wrong. Let's say that we have the following circuit. Oh, wait, this isn't the really hard one. But okay, let's do this one and then we'll do the hard one. So I have my generic differential pair, but I have some parasitic resistance. That parasitic resistance is occurring at both inputs so that I still have symmetry. All right. So what's my half circuit going to look like? Let's start there. That should be our starting point for pretty much all of these, okay? So I have my input signal, VN1, that's being applied at the base. My emitter is grounded. I have some resistance RP connected between my collector and ground. Here's the node where I take my output. There's my resistor RC. So what's my gain going to be? Based on just what we've done in this class to this point today. AV is equal to negative GM, let's call it Q1, so GM1, in parallel with R01, in parallel with RP, in parallel with RC. By infection, right? We know that this resistor RP is placed between the collector and the emitter, which places it in parallel with R01. And based on our prior experience, we know that R01 was in parallel with R0C for this simple common emitter amplifier. No need to do any real work whatsoever, right? So should be fairly trivial. Let's screw everything up. All right, so this is different than anything that we've looked at before because we're taking our output signal at the base of those transistors. I guess I should label my transistors. So let's call this guy Q1, Q2, Q3, and Q4. So my differential output is measured from the base of Q3 to the base of Q4, right? So pretty different than anything that we've done, but it's still a differential amplifier and it's still perfectly symmetrical. So we can do everything that we've been doing to analyze this guy. Now I will say that doing the short circuit transconductance and then the output resistance for this guy, in my opinion, is harder than just measuring the output resistance, the voltage gain directly. And I'll explain what I mean by that in a moment. So let's look at our half circuit, right? So we have VCC, our parasitic resistance. Here's V out. Here is V in. Here is Q1. Here is Q3. Again, this one looks nothing like anything that we've seen before because we're taking the output there at the base. If we were taking the output at the collector of Q1, this one would be significantly easier, but unfortunately, that is not the cards that we've been dealt. So I am going to draw my full-on small signal model for this guy. So here's V out 1. R pi 3, V pi 3, GM 3, V pi 3, R naught 3. So this is transistor M3. My collector is tied to ground. This is they're both, I didn't draw this one right here, but they are both NPN transistors. Also, I have that resistor RP between my base and ground as well. And so I'm going to realize that like so, because that's between my base of that transistor Q3 and ground. So that seems like as good a place as any to put it. For transistor 1, here's GM1, V pi 1, here's R naught 1. V pi 1, R pi 1, Vn. And I know that the emitter of transistor 3 is connected to the collector of transistor 1, like so. And I'm going to call this node X. And I'm going to call this node Y. All right, and node Y is obviously just our output voltage. Yeah. So what I'm going to do here is my goal is to get V out in terms of Vx and then get Vx in terms of Vn, effectively treating it as two distinct stages that will allow me to use the gain relationship. V out divided by Vx is multiplied by Vx over Vn gives me V out over Vn. So just like I did for an awful lot of the circuits that I did in 335, doing the exact same approach here, okay? So I'm going to start by writing KCL at node Y. All right, so at node Y, I have V out 1 minus Vx over R pi 3 plus V out 1 divided by Rp is equal to 0. That one is easy enough. I can rewrite some things here. So I'll do it down here. I can say that V out 1 times 1 over R pi 3 plus 1 over Rp is equal to Vx over R pi 3. And so I can say then that V out 1 is equal to Vx over R pi 3 multiplied by R pi 3 in parallel with Rp. Which gives me Vx multiplied by Rp over R pi 3 plus Rp. And for the sake of argument, I can divide V out by Vx, and I now have the transfer function for that stage, right? So I will write that down explicitly. V out 1 over Vx is equal to Rp over R pi 3 plus Rp. Now, if I do KCL at node X, I'm going to have so what I'm going to do here, just so that I can be specific about the equation that I'm about to generate, I'm saying that this current flows in, this current flows in, this current flows in, and this current flows out, and this current flows out. So I'm going to add all the ones in green together and set them equal to the sum of all the ones in red, because that's how current law works. So I just want to be clear about what I'm doing. So V out 1 minus Vx over R pi 3 plus GM 3 times V pi 3, which is again V out 1 minus Vx over R naught 3 is equal to GM1 times V pi 1, where we can easily see that V pi 1 is the n, plus Vx over R naught 1. And so now, one thing I can see is that I have a couple of instances. So my goal with doing KCL at node X is to have only terms with Vx and Vn, so that I can get that transfer function relationship for that particular state. Right now, I have a couple of places where I have V out 1 minus Vx, but I know that V out can be expressed in terms of Vx. So one thing that I want to point out to make our algebra a little bit easier is that V out 1 minus Vx is Rp over R pi 3 plus Rp dx minus R pi 3 plus Rp over R pi 3 plus Rp dx gives me simply negative R pi 3 over R pi 3 plus Rp dx. So if I substitute that guy in, what I get is negative Vx over R pi 3 plus Rp. Then I'm going to have minus GM 3 R pi 3 Vx divided by R pi 3 plus Rp minus Vx over R naught 3 minus Vx over R naught 1 is equal to GM1 Vn. Now, obviously, I can factor out the Vx's on the left-hand side. So this is going to leave me with Vx multiplied by 1 over R naught 1 plus 1 over R naught 3 plus 1 over R pi 3 plus Rp plus, and so this is where I'm going to do something a little bit strange here. It should be pretty obvious that I'm trying to make all these look like they're in parallel with each other when I move it to the other side. So I'm going to have to do a little bit of algebra here. So when I do the reciprocal of this guy, I'm going to have R pi 3 plus Rp over R pi 3 times GM3, which looks like 1 plus Rp over R pi 3 times 1 over GM3 to the negative 1. So I'm going to put it in parallel with that is equal to negative GM1 Vn, and from this, Vx over Vn is negative GM1 multiplied by R01 in parallel with R03 in parallel with R pi 3 plus RP in parallel with 1 plus RP over R pi 3 times 1 over GM3. Now I can say that my voltage gain AV is equal to V out over Vx multiplied by Vx over Vn, which gives me negative GM1 R01 in parallel with R03 in parallel with R pi 3 plus RP in parallel with 1 plus RP over R pi 3, 1 over GM3, all this multiplied by RP over R pi 3 plus RP. Breaking it up into two stages. Again, I feel that this math was less tedious than doing it the other way, where you have to calculate the output resistance, which isn't particularly difficult. Calculating the short circuit transconductance was just as much work as calculating the gain here. So I thought that calculating the gain directly would be an easier path. I did it both ways, but for time constraints, this way seemed easier. And if you are one of those people that work problems in the back of the textbook, you will actually see stuff like on some of the problems, it'll give you a couple of circuits and it'll tell you, in some instances, calculating it using the short circuit transconductance may be easier than calculating it directly and vice versa. So unfortunately, there's not a hard and fast way to tell which is going to be the easiest route for something weird like this. But this is the, in my opinion, the hardest problem you would ever see on this type of material. And we just knocked it out in less than 20 minutes. So, all right. I feel pretty strongly that we have a reasonable grasp on BJT differential pairs. There's really not too many different iterations that I could do. I guess one other thing that I want to talk about real quick before we move along to MOSFET. What if I had a BJT differential pair, RC, plus VOD minus RC BM2. All right, so let's talk about two quick cases here. So this is our basic guy. What if I said that we no longer had an ideal current source? Instead, our current source does not have an infinite impedance. It has some finite impedance, RED. Does this fundamentally alter the way that we have to analyze the circuit? Right, so it's along that point of symmetry. So effectively that resistor looks like it's grounded out. So that resistor REE doesn't do anything. What if instead I had this? How does that change things? Sorry, what was that? Yeah, so I would literally just have a degeneration resistor in my half circuit. So I would analyze it as if it were a common emitter amplifier with emitter degeneration. That's it. Something you did 3 months ago or whatever it was. Nothing. That's as hard as I can screw with things here. Okay. You might see something maybe in a homework problem or potentially in your test. I'm saying that completely without having looked at the test at all yet, because I'm supposed to talk to Dr. Patari about it later today. But you might see something where, just for the sake of argument, we had some resistor R, like so, between those two things. So our output resistance would effectively be the voltage drop over that R. How can we construct a half circuit for this guy, just off the top of your head? Anybody got any thoughts? So you just break the resistor in half to make it symmetrical, right? So put R over 2 on the left-hand side and R over 2 on the right-hand side, and you now have a symmetrical circuit that you can analyze. So that would be a common emitter amplifier, in this case with emitter degeneration and a fixed load resistance. That's it. So in this guy right here, we know, let me be more specific here. So we would take that resistor R, split it up as R over 2 over here, R over 2 right here. The voltage at that node, X, has to be 0 because it's on the axis of symmetry for the circuit. So our half circuit for this guy, here's RC, here's V out. In, here's REE over 2. And here's R over 2. So it's effectively would be very similar to what we did when we had the parasitic resistance earlier between the collector and the emitter, but in this case, we have that emitter degeneration as well that we have to pay attention to. Can't make these things too particularly difficult and still be able to be analyzed. We will be working a circuit where we no longer have symmetry. I think it'll be next Monday, if I'm not mistaken. That's when we do a differential pair with an active load. And what that active load does is it turns our differential output into a single-ended output, which means we're effectively going to turn a differential pair into a true single-stage op-amp. And we do it with a current pair. It's nothing too wild, nothing you haven't seen before. All right, Mosfets. So we got something going on like this. Here's RD. Here's M1, BN1, here's M2, B out 1, B out 2, here's our other RD. I'm sorry, that's supposed to be a current source, ISS. All right. So, small signal model. What do you think the voltage at node X is going to be? 0. We don't need to derive it again, do we? It's going to be the exact same derivation we had before, except that we aren't going to have any r pi's to worry about. So for the literally the exact same reasons, we should see that node X is at 0 in both the large signal and small signal model, which allows us to construct half circuits, which allows us to analyze these guys as the simple amplifiers that we've all been dealing with since 335. So my half circuit for this guy would be RD out. Looks too much like a BJT. Handwriting is getting quite sloppy. I apologize. So what should our gain be? Common emitter amplifier with a Mosfet. What's going on? How is it different from the common emitter amplifier with BJT? It isn't. Negative GM 1, R naught 1 in parallel with RD. Same damn circuit. We could do other weird and wacky things to try to screw with it, but we're going to get the exact same results that we did with the BJT. So if you kind of know what's going on with the BJT, once you get that clicking, the MOSFET is literally a joke to do because there's less stuff to worry about. Excuse me. All right. Any questions? We went through stuff reasonably quickly. Hopefully the math wasn't too particularly terrifying or anything like that. If it is, feel free to yell at me. Not, I guess I'll see you guys on Friday, where we're going to talk about cascoding these guys, which we could probably cover in 10 minutes.